Okay, BCers, what do we know about logistic growth? Right, that's the question we're going to find out today. And if we know where the point of inflection is and what the words carrying capacity means and things like that that are basic to logistical growth. Okay, so here we have our equation about fish living in a pond. Okay, so our graph, right, logistical graph, starts with your initial value, P of 0, right, when time is 0. So this is our time axis, and this is our population axis. And the population is going to max out according to the environment, right? There's only so many resources for these fish to consume. So L is the maximum amount of fish that can live in this pond. Okay, and what's going to happen is logistically we're going to increase up to a point of maximum growth, and then we're going to grow but at a decreasing rate until we reach that horizontal asymptote of L, which is called your carrying capacity. Okay, that's the biological word, capacity. That's the amount of organisms that can live in an environment given the resources that are there. Okay, so this is our point of inflection. We will notice that this always happens in the middle of your carrying capacity and 0. Okay, not P of 0, but literally 0 animals, 0 organisms, 0 fish. That's always half of L. This is your point of inflection. Okay, we have to create an equation to figure out when that's going to happen. But basically that point is half of your carrying capacity, is when the rate of maximum growth is occurring. Okay, so we're increasing, we're concave up to this point, and then our graph is concave down. It's still increasing, but at a decreasing rate. Okay, what are some other things that are good to know? We have a ratio. If we compare K over L, okay, that's going to be our ratio that we're going to be looking at. K is your constant, right? These are all constants of proportions and some growth rates. Okay, so here we have our equation, 8p minus 0.02p squared, with our initial condition of having 50 fish to start with. That's the population at the beginning. Okay, so this number, right, this is a form of an equation that you should recognize. Kp minus, let's see, K over L or something, and then P squared. So K is going to be 8 in this case, and we need to write this as some type of a fraction. Okay, so K over L, where K is 8, equals 0.02. What is 0.02 as a fraction? This is 2 100ths. So in other words, that's 20 divided by, 1,000. Or, I guess 2 over 100 is okay. We could write that, 2 over 100, right? 0.02, 2 100ths is 2 divided by 100. So what I've done is we've taken this decimal and we wrote it as a fraction, right? So K over L, this ratio, has to be equal to this decimal if we know that K is 8. This is going to help us find L, which is the answer to this question, right? The limit as t goes to infinity. This is asking you about the horizontal asymptote, aka the carrying capacity. Okay, but they won't say, well, they might say what is the carrying capacity, or they might use the mathematical notation. the limit as t goes to infinity, right? We need to know that's a horizontal asymptote. So let's come back over here and solve this for L, since L is your maximum carrying capacity. 2L equals 800, so L equals 400. Okay, so in the context of this problem, that would be 400 fish that are able to survive in this pond. So let's answer some more questions. What's the range of our solution curve? So we started at how many fish? 50. That's the minimum amount of fish that we're going to have. And our maximum amount of fish is 400, right? That's your L value. That's your carrying capacity. That's the maximum. Less than. Okay, because if it ever gets to 400, then we'll start having fish die. So less than 400, that's your horizontal asymptote that the amount of fish is going to be approaching. For what values of P is the solution curve increasing? Okay, so we're asking right now about this point of inflection. So we decided our carrying capacity is 400. So how many fish will there be at the point of inflection? That would be 200. So our graph is increasing from 50 to 200. Right? Our slopes are positive. And then our slopes are decreasing from 200 to 400. Okay? So from your minimum to your L over 2, right? It's about the half of the carrying capacity is where we're going to start having it be concave up, and then after L over 2, our graph is concave down. Sorry, the population. Our population is always increasing. Okay, so it's increasing from 50 to P because P is never decreasing. Okay, that's what happens with the logistic curve. Okay, so dP dt, right, that rate of change is always positive for all populations. Okay, now this next question is asking us for when is our curve concave up and concave down. So that's what I was talking about up here before. Concave up on the blue interval and concave down on that pink interval. Okay, concave up. So our population of our fish is always increasing. We're always getting more and more and more fish up until we reach close to 400 fish. But for concave up and concave down, we have to include this point of inflection, or your half of your carrying capacity. Okay, so L over 2, right, the point of inflection is going to happen when the population reaches 200. So that's the maximum growth rate when the population is 200. Before then, it's growing, and then after that, it's growing, but not as fast. Okay, so that's the point of inflection. It always happens at L over 2. Okay, and concave up from 50 to 200, and concave down from 200 to the carrying capacity. Okay, the next two saying, well, what if we start with a different initial population? Okay, what changes then? Let's talk about it. So here's the graphs of our next two problems. We start at 300, which is above the midway point, right? Above our point of inflection. So no points of inflection. Our graph is always increasing, and it's always concave down, right? Because our population is above the point of greatest growth for our L of 400. Okay, and then if we start at 500 fish, our fish are going to die because there's too many fish and not enough resources until we reach about 400 fish. So the graph will always be concave up, and our slopes are always increasing, right? We're decreasing at the beginning. Lots of fish are going to die, and then not as many fish will die, and then fewer and fewer fish. The rate of death of our fish will decrease. Okay, so it's important to understand where we are starting. Are we starting at a small number or are we starting at a large number? And how is the growth happening? How is our logistical growth happening? Okay, let's look at a problem with another equation. Oh, with some solving for P. All right, animals, a population. We don't know what the animals are, but here is their growth, right? The logistic differential equation. So we want to figure out what is our L value and what is our K. Well, it gives you L right here. This is one of our forms. This is the L minus P form of our equation. So L is going to be 100. That's the amount of animals that could happen. And K is going to be, well, if we distribute this, what is 100 times 0.01? I believe that's 1. This is 1/100th times 100. So we have a K value of 1 and an L value of 100. So our K is 1/100th, right there, 0.01. Let me erase. 1/100th. P of 0 is 20. Solve for P as a function of T. Okay, we know the population is 20. We know the L is 100. K is 0.01 and T is 0. Okay, so we know everything except for B. So we're going to do our little math in order to solve this equation for B. Okay, well, negative 0.01 times 0 is 0. E to the 0, that's 1. So this becomes 20 equals 100 over 1 plus B. So multiply by 1 plus B, and then divide by 20, and these guys switch places. 1 plus B equals 100 over 20, which is 5. So when we subtract 1 from 5, I get a B value of 4. So if we come back up, P equals 100 is our L, your carrying capacity. 1 plus our B value is 4. E to the negative 0.01 T. So our next question says, what's the population after 3 years? So we're going to replace T with 3 and plug this into our calculator, because that's not easy to do in your head. So we don't have much growth after 3 years, just 20 animals. Now, when will it equal 80? So here's our algebra problem. We want to know when 80 will equal 100 over 1 plus 4e to the minus 0.01 t. Right? Solve this equation for t. So here is our algebra that we're going to do. We take this denominator and we switch it with the 80. Right? We multiply by 1 plus 4e, and then we divide both sides by 80. So in essence, we are just switching our denominators. So that's our little math hack. 100 over 80. Okay, 100 divided by 80 in our calculator, 1.25, right, minus 1 is 0.25. Divide that by 4, right, to get rid of the and that's 1/16, right? Because 1/4 divided by 1/4 is 1/16. And then here is our fantastic thing. We're going to take the natural log of both sides. Okay, the natural log of e is, of course, 1, so this just becomes the exponent. And then our last thing will be divide by negative 0.01, which is fine because the natural log of a fraction is a negative number to begin with. So a negative divided by a negative, that's going to be a positive. How many years? 277.3. Okay, so that's the algebra that we use if we ever want to solve this for t when the question asks when will there be so many animals. Okay, so we need to really recognize our forms of the logistic equations so we can figure out what our k values are and your p values before we start everything else. Okay, goodbye.